Hi, I'm Stijn Nomus, and today's lesson will be about projection of an ellipse. So the projection of a 2D object, an ellipse, on a 1D line. And it's going to be an orthographic projection, so it's a very simple case. I will explain it later. And again, as in many lessons, we're going to apply rational trigonometry, and that will make life easier, as it turns out. And what I'm interested in is the size of the projection of the ellipse. And you will see that it will be expressed as a semi-quadrance P. And it turns out the proof is quite a long derivation, but in the end we get a really simple formula. So let's go back to a perspective projection. So we have a point in 3D, x, y, z, and it projects on an image, on a image plane, and then you get a coordinate x, y, and here we get the formulas. But today I'm going to talk about an orthographic projection, and you can think about that is that the camera point is going all the way to infinity, and the focal length f is going to infinity, and then the three-dimensional point x, y, z projects on a plane simply as x, y. So basically we get rid of the z, and we basically equate small x with big X and small y with big Y. And today I'm making it even simpler, because we're going to project from 2D to 1D. So in this case it's a circle, and it projects on the line Y on the left as that red line segment. And if you remember that circle has a radius expressed as quadrants A, it simply projects on the left as on that line segment. I call it the semi-quadrance A. So I'm not interested in the whole, the length of the whole line segment, but half of it. And in quadrants terms, that's not half, but it's a quarter. So that's why I call it semi-quadrants. So simply the radius of the circle is also the size of the projection. But now we're going to the ellipse. That's a more interesting case. And we have to define a couple of things. So it's an ellipse with a major axis, that's the length, and a minor axis, that's the width. And I express the major axis as quadrants A, and the minor axis, well, semi-quadrants B. And A in the following slides, A will always be bigger than B. And then S is the spread between the major axis and the viewing direction, so basically the z-axis. And what I'm interested in and what I'm going to derive is a formula for P. So if you change A, B, or S, how does that affect the P? And I will give you the answer. It's a very lovely, simple formula. P is S times A plus 1 minus S times B. And it's simple, but it's not trivial, as we will see. So let's go to a familiar XY coordinate system and put our ellipse aligned with the major axes are aligned with the coordinate axis. A is always bigger than B. And then for a standard ellipse with center of the ellipse at 0, 0, this is the equation. So x squared over quadrants A plus y squared over quadrants B is equal to 1. Now let's look at a tangent line. So that's a line that touches the ellipse in one point, and it gives the orientation of that little line segment there. And we call the point, the tangent point, x, t, y, t. And it turns out there's a simple formula for that line, for that orange line. Xt over a times x plus yt over b times y is 1. And it's a linear equation, simple linear equation for that line. And remember that the point xt, yt is also on the ellipse. So it's also described by the equation of the ellipse. So we have to keep that in mind because we're going to use that fact later. So now let's look at the points that are the intersection points between the coordinate axes and the tangent line. And for example, if you set y to 0, so then you get the intersection with the x-coordinate line, or the x line, then it's x is a over xt. So the coordinate is a over xt, comma 0. And similar thing for the other points. Now I'm gonna define two new quadrances, G and H. And G is from the 0, 0, the point in the middle, to that intersection point, and H is the other one. And if we express the quadrances, it's simply the square of one of the coordinates, or actually the square of both, but one of them is 0. So G is a squared over xt squared, and H is b squared over yt squared. Next step, I'm going to take a line that's perpendicular to the tangent and goes through the origin. And then immediately we get the quantity that we're interested in, the p. The p is the altitude from the origin to that intersection of the tangent and this line. So we also need spread s between the x-axis and the tangent line. And because that triangle is a right triangle, the opposite spread is 1 minus s. And now we can apply the spread law from rational trigonometry. So if you look at the smaller triangle on the right with p and g, so if we apply the spread law, is 1 over g is s over p. And similarly for the smaller triangle on the left, it's 1 over h equals 1 minus s over p. So it's simply applying the spread law. So what does it give us? This gives us two expressions for p. It's sg and it's 1 minus sh. So we're going to use that. So let's remind ourselves what g and h are on the left. So these are the long quadrances. And use our formula that we just derived, filled it in. And then we get something like this. And let me clean that up a little bit. So now we have an expression 1 minus s times b squared over yt squared is equal to s times a squared over xt squared. And you can see that the g and the h are gone now. And the next step is reminding ourselves that our tangent point also is on the ellipse, so we can use the equation on the bottom right. Put that all together, and now we get expressions for xt squared and yt squared, and that turns out to be useful. Let me do a side remark that we can also find the quadrants between the origin and the tangent point, and that's this nice expression here. We're not going to use it today, but I thought it was a nice intermezzo. So going back to our xt squared and yt squared. So this is xt squared, and remind ourselves of p is s times g. So let's fill in the g that we found earlier, and now we can fill in the xt squared. And you can see it appear. So now we get this very simple result, sa plus 1 minus s times b. And similar thing for the other one, the p is 1 minus s times h. So what do we have now? So for this ellipse, with a tangent that has a spread between the tangent and the major axis of the ellipse S. The P is simply S times A plus 1 minus S times B. And we don't need a coordinate system anymore. And we can even define the line through the origin and then change the S a little bit. So now it's really the viewing direction, the spread between the viewing direction and the major axis. Now let's shift the P outside of the ellipse, get rid of that. And now we have a projection, an orthographic projection of the ellipse. And let's go with this marvelous animation. So now we're back at the original illustration, and P is S times A plus 1 minus S times B. And this is not a trivial result. It's mathematicians are talking about this when results are not obvious. So when a proof takes quite a number of steps, as we've seen. And there is no, as far as I know, there's no short algebraic proof of like one line or something. And I'll give you a counterexample that I've taught in another lesson. So this is the visual spread of a circle. And here we can simply apply a definition. So the spread P is simply the opposite quadrants over the hypotenuse quadrants. And we can see a right angle here, right triangle here. So P is simply A over D. So this is a trivial result, and you can do it in one step. So let me show you some examples. So on the left and the right you see an ellipse, but on the left the view is from the left, and on the right the view is from the top. So these are the extremal views, and if you look at the P down below, on the left P is 1, minimal, and on the right P is 4. And if you get the intermediate case for S is half, then P is 2.5, if you just simply apply the formula. So now on the left, on the right, I have a less extreme case. On the left, S is a quarter. On the right, S is 3/4. And you can see P is going up from left to right. If I do other objects, like the A and B are different. On the left, A is 4 and P is 0, so now it's a line segment. And you can see in this case P is 2. On the right, A and B are the same, so now it's a circle, and P is 4. So let's look at the relation between S and P. So let's start with the ellipse case in the middle. So it's a straight line, and it starts at on the left at B, and then it goes linearly up to A for S is 1. And on the left case for the line segment, the smallest P that you can get is 0. If you look at it from S to 0. And on the right, you can see for a circle that it doesn't change at all. So every viewing angle gives the same P. So what do we have? I derived for you a very simple formula, another simple formula, all thanks to rational trigonometry. We get all these simple formulas. Although this time it's not a trivial case. It took us quite a number of steps to get to actually complete the proof. And I've shown you a couple of examples, but what I haven't told you, I'm going to tell you now, is that this turns out to be very useful for deriving results in 3D vision. So I'm going to talk about that in future lessons. So thanks for watching. If you have a question or comment, put it down below. Or if you want to contact me directly, you can go to my website. That's right there. All right, bye-bye.